And people who are more paranoid about their health are probably also going to be taking better care of their health, right? And so it might actually be that you got things going in the opposite direction. In that case, the cost curve would be increasing. Because the people who want insurance the most, the people who are the first into the market, are the least costly. And the people later into the market are more costly. That's called advantageous selection. Now we're going to return to the policy implications of this stuff later in the course. But in the meantime, I want to consider an estimation of this by Einov et al. In 2010. And what they did is they looked at a large company, and different divisions of the company had offered different prices for insurance, and therefore had gotten a different fraction of the employees to sign up. And they assumed that this was more or less randomly assigned. And they used the variation in quantity that you got out of that and the amount of health claims that the people had to figure out what the cost was of insuring different fractions of the population. So here's what they got. They basically had prices randomized over here, and that led to these different demand points. And that, in turn, allowed us to see what was the cost, on average, of covering people when this fraction of the population accepted coverage. And then they derived from this marginal cost curve, and that let them say how much more costly was it to cover someone who was like the first person in versus someone who was later in. OK. So one thing to note is that neither this picture nor this picture looks exactly like the standard shape that I drew over here with these U-shaped curves, right? And one reason for that is that we didn't have any fixed costs. And there was no necessary reason why things should have decreasing returns. If we assume that there's fixed costs and then decreasing returns, we're always going to get a shape that's like this. And the standard story for this is that, well, there's a fixed cost of setting up a business. You know, an entrepreneur who has to manage a whole thing gets spread thinner and thinner as you have a bigger firm. And therefore, it starts getting less efficient because he can't take as good care to make sure that things work out well. So let's consider a simple example of that. If we have a Cobb-Douglas production technology, but we have a fixed cost, and the Cobb-Douglas production technology is homogeneous of degree less than 1, then we're going to get increasing. We're going to get initially decreasing and then increasing costs. In particular, let's consider the cost function where there's a fixed cost plus this version of the Cobb-Douglas thing. Now remember, the Cobb-Douglas had a whole bunch of messy coefficients in front. But we don't really care about any of that, right? All in the end we care about here is what returns to scale it is. And that's the beauty of thinking about things in terms of cost rather than thinking about them in terms of the production function, which is that all that messy stuff gets summarized into just some number that you put in front of this and some power that you raise it to. OK, so we can now just calculate all the things we talked about before. So the average fixed cost is the fixed cost divided by S. The average variable cost is this part, the variable cost, divided by S, the score that you were achieving. The average cost is just this whole thing divided by S, which is the sum of these two. And the marginal cost is just its derivative, which we bring the gamma out in front, and then we have to the 1 minus gamma minus 1 here. OK. If we set the fixed cost equal to 1, the k in front equal to 1, and the gamma equal to 1.5, which gives us decreasing returns to scale because, sorry, it gives us, yes, it gives us decreasing returns to scale because costs increase more than linearly. When we increase the score that we need to get, we get the standard shape. So here's the average fixed cost, and here's the average variable cost. The total average cost is the sum of those two things, and the marginal cost is increasing, dragging up the average variable cost, and first dragging down the average total cost, but then dragging it up as it goes above. OK. So this standard assumption, oh, I think I had some Mathematica code where we could play with this. Let's see. Where do I have that? Here we go. Okay, so this is a simple form that we can just plug into Mathematica. Okay, so this one I've made have actually increasing returns to scale so that the all the costs are going to decline through the full range. So this is the average cost. This is the average fixed cost. This is the average variable cost. Where's the marginal cost? It's got to be dragging all this stuff down. Yeah, but that seems to be above the green at some point. Yeah, the blue must be the average fixed cost. The green is the average variable cost. The purple is the average.
No, blue should be average fixed. No, pink should be average variable.
Pink is average variable. Green is marginal, and then yellow is average.
Don't the marginal and average variables start at the same spot then?
No, not necessarily. Not if they're coming down from infinity. So because they're sort of at the same spot at infinity, right? But then they're coming down. But we usually think that things have maybe decreasing returns to scale. So that if we put this to be 1.1, then we're going to get more that U-shaped cost curve that we get. And as we make it increasingly worse returns to scale, we're going to get this much more rapidly increasing costs. As we make the fixed cost component larger, it takes longer for the value of the economies of scale we get from spreading the fixed costs over a wider range to diminish. So if I were to increase this to 10, you see the point that's the minimum of the average cost shifts over. As we make the technology less productive by increasing the multiplier, all the costs just rise. Anyway, that gives you a little bit of a sense of how you can play around with these things using mathematical software. Okay, so the standard assumption is based on the idea that we have these fixed costs and then we have decreasing returns to scale, and therefore the AC first declines and then increases. You have this U-shaped cost curve. On the other hand, if AC is declining over the full range, maybe because the fixed costs are just so big or something like that, we call that economies of scale. Now, what are some of the reasons? Is Cheng Yi here? Yeah. What are some of the reasons for economies of scale?
You mean reasons we call it, or reasons it
Well, it exists in the real world.
Well, perhaps because it's more efficient when you put more factors of production together.
Mm-hmm.
For example, well, if we have computer programmers, maybe if we put two of them together, they can discuss and actually increase both the co-writing schemes.
Mm-hmm.
And or perhaps if we're in a assembly plant,
Yeah.
more machines actually leads to faster production and will be better than if you put different machines upon.
Yeah. So one reason is just that there are fixed or lumpy costs. So one example of this is there's this restaurant called Andres Carnes de Res in Bogota, Colombia, and it's an absolutely enormous restaurant. It's probably a restaurant for like, I don't know, could probably see 2,000 or 3,000 people. And they have all this stuff there. They've got like a giant dance floor. They've got like a place for kids to hang out. They've got like a little movie theater there. And there, you couldn't do that in a normal restaurant, right? Because you just don't have enough people there to do it, right? But you can spread those types of fixed costs over a lot more people, and so you can get like a really amazing restaurant in some ways if you can spread those fixed costs over lots of people. Another reason is specialization. And I think this is sort of what Chengyi was trying to get at, which is that if you put a lot of people together, then each person can do a very, very tiny task and really master that task, rather than someone having to do so many different things in an inefficient way. So that's another reason why you can have economies of scale. A third reason, and we'll look at an example of this in data in just a second, is that there can be what's called learning by doing, which is very related to this, which is that it's not just that I can be focused on one thing and not get distracted by other things, but if I spend a lot of time doing something, I can get much better at it. And so if you produce a lot of things, then over the time you get better at them, and therefore there are sort of intertemporal economies of scale. That is, if I do a lot, I'm in the long term better at it, right? I think this is the reason why over the course of someone's lifetime, they usually focus on one thing, because there's sort of economies of scale in doing that thing, because they get better at it every time they work on it. Another reason there can be economies of scale are network effects. If people like to interact with a lot of people, it makes a lot more sense to provide Facebook to everyone in the world rather than to provide one Facebook to a few people, another Facebook to other people, because the interaction of all those people generates network effects. Another reason you can have economies of scale is because of adverse selection. And this is something we were just talking about now, right? If you serve more people in the insurance market, your costs get lower because the most expensive people are the first people into the market. On the other hand, if we have increasing marginal costs, we call that diseconomies of scale. And is Jing here? Yeah, Jing. Why might we have diseconomies of scale? Don't look at the slide.
Because in the real world, some input must be fixed. For example, if it's a factory, the size of the plant or size of the production space must be fixed. So as you increase the number of workers or other inputs you put in the factory, some problem may arise. For example, if there are too many people, there may be extra administrative costs, which will somehow increase the marginal cost.
Yeah, or they could just get really crowded in there, right? Or there could be one manager and he has to look over so many people that he can't keep track of all of them, right? So another problem is that you might have to monitor all these people. And that's similar to the entrepreneurial thing. Like, how do you make sure that everyone's doing their job if you have so many people around? And this is a huge drag on the development of companies in poor countries. Because the problem, as we said in the other lecture, is that people might only trust people in their family not to steal from them, right? And that might be a reason why it becomes very expensive to expand your business, because the set of people who you trust and can rely on runs out. Another reason, which was the reason why we got these increasing marginal costs in the picture about the search auction, right, is that it's cheaper to get the first few clicks than to get later clicks, because as you start getting more clicks, you're having to bid increasingly high for that, right? And that's because basically you have market power. How much you bid determines how many clicks you get, and you are basically raising it by putting more competition with yourself into the auction by raising your price, right? So we'll talk a lot more about that when we do monopoly. Now, despite both of these things, a very common assumption is constant returns to scale.